Hello, my name is Michael Kragness, and I am the applications scientist at AMETEK MOCON, and I would like to thank Converters Expo South for the opportunity to speak on this platform. Today's discussion is about water vapor transmission rate testing and the critical role that it plays throughout different industries. Let's start from the foundation and discuss the permeation mechanism. As you can see here, the barrier, this could be a flat film, it could be the sidewall of a container. You have the outside atmosphere, which wants to get inside of the packaging. So there's a concentration gradient that is actually driving this permeation mechanism. And this only correlates to structures that are non-porous. So things that are more breathable or actually have holes in them like perforation, it would not be the same mechanism. So you may ask yourself, once you have some packaging, which test is best to measure the water vapor transmission rate? In so many different products and industries, there's a very wide range of moisture barrier needs. You have your breathable structures such as PPE in diapers, which must allow for high moisture transmission. Your quality for things such as food and beverage, and also pharmaceutical drugs. Even extremely high barrier studies for electronics and photovoltaics that need such a high barrier to moisture that you may become somewhat limited in your options to characterize these materials. And then, of course, you have certain industries that that will tell you which tests that you have to use to actually comply with the industry standards. So as you can see from this table here, it lists a number of industries and it's placing them as far as water vapor transmission rate needs. So kind of in the middle, you see the packaged foods and the pharmaceutical industry. Then at the fringes for a very low water vapor barrier, you see your non-wovens and your breathable materials. And then for extremely high water vapor barriers, you have your OLED market and also your flexible electronics and photovoltaic materials. So as you could see, with such a vast range of water vapor transmission and what is actually suitable for your product, you can imagine that there will be different tests that you may have to perform depending on what level of transmission is needed for your specific product. As I said before, industry regulations can dictate what tests you will have to meet the requirements. For example, EPR requirements, CGMP requirements. The U.S. Pharmacopoeia actually has certain test requirements for testing their blisters and drug containers. For photovoltaic materials, you also have certain standards of tests that are deemed necessary to collect the information needed to verify your not only your shelf life but the functionality of either your product or your system in some cases. So after you can determine which tests you may need to measure your water vapor transmission rate, what are the test conditions or what are the challenge conditions for your test? So you'll want to think about your supply chain. What are the rigors of your supply chain? How is it going to get in front of your customers? How is it going to be stored? How is it going to be transported? How is it going to be sealed in the manufacturing process? What is the environment? These are all things that when you're designing a package barrier, you should think about because it's not just the end application. For instance, if we're discussing room temp with moderate humidity inside of a supermarket, The products, what did it take for them to get there? Did they have to fly in a plane or take a long trip over the sea in a very high humidified environment? Or were they transported in via semi in a very hot, humid environment in the summertime? So you'll want to think of the most challenging environment that your package will face, and depending on the time that it spends in that environment, you can fine tune what your barrier needs will be to water vapor. Now, let's move into discussing some different test methodologies that are used for these different transmission rate levels. So for our very low barrier products, such as diapers, PPE, and other breathable applications in the non-wovens market, currently they are actually removing the forever chemicals that are within some of the layers in the PPE. This is something that has been going on more recently, so more testing is needed as these materials are made to be more safe since they're coming in contact and being worn by people. And these structures are porous. That being the case, there's a different test methodology that we would take to gather the water vapor transmission rate for products such as these. So historically, the cup method, are known as ASTM standard E96, that was used for very high transmitting water vapor materials. But there is something specific with that method, whether you're using a wet cup or a dry cup, that once you get to a certain transmission rate level, a lot of questions arise. Questions like, if so much moisture is going through my material, how can I be sure that I'm really challenging one side with 100% relative humidity? And how can I be sure, conversely, that the other side is dry when so much moisture is moving into the dry environment? And this was something that had to be addressed because the need for such high breathable, high water vapor transmission rate materials were needed. And to get accurate results, there was an instrument method created that actually is similar to a upside down cup test, where the liquid water is actually in contact with the barrier film. And what that does is that allows you to know that you are going to be at 100% relative humidity, because there's no gap in between the water reservoir and the actual material, versus the E96 cup test, that traditional method, there was a gap, and that was always in question as to what the driving force was. This is more so for non-wovens and breathable materials, and actually some very high transmitting materials used as venting. Sometimes you want to let a lot of moisture out as a vent so it doesn't pressurize a package system. Now, that brings us to another industry that is also has very high transmitting materials. In the underlayments materials and construction materials and geothermal barriers, these actually have the need to not allow any liquid water to pass, but to readily allow moisture vapor to pass. And also perforated films. For instance, if you buy something at a deli and it's hot, you may receive the food in a container that may have a perforated film, which is allowing, some of that steam to escape while still keeping the food hot. These materials can be somewhat difficult to test, so there's a certain approach that will have to be taken so we can be accurate and repeatable. So ASTM E96. So this is a good method up until, I would say, 8 to 10,000 grams per meter square per day. Then that's where this still air gap that you can see in the diagrams here, So you have your dry and your wet cup, and then you have a gap, and then you have your barrier sealed to the top of the cup. So once you place these in a humidified environment, you're either going to get moisture that's moving into the cup or out of the cup, depending on if you're using a desiccant or the water method. And this is a good method for things that transmit, high but not extremely high as in the previous case. And what's good about gravimetric testing is if you have a good analytical balance, it's reliable and it's repeatable, and you can do a lot of samples at once versus some instrument methods. So you get a large data comparison. And one of the things that is not a benefit is these tests generally will take longer and you're really limited by the sensitivity of your balance. So this brings us to the next test method, which focuses more on medium to high barrier packages. Things like food packaging, medical device, flexible pouches, blisters for pharmaceuticals. All of these fall within that range, and ASTM F1249 is a very robust standard that has a very wide serviceable range for testing. I would say this range has the highest percentage of package testing for water vapor. So ASTM F1249, this is a schematic of a diffusion cell to where you have your barrier film in the middle, and in one chamber we have controlled RH, and then in the other chamber we have dry nitrogen. As the moisture passes through the film, the dry nitrogen sweep takes it past the pressure modulated infrared detector, which is converted into grams of moisture through your barrier material. And this is a very robust method that is more sensitive than the E96 method, and it's also more repeatable due to the sensitivity that we get from the pressure modulation of the infrared detector. So now moving into the high barrier water vapor needs here. Flexible electronics, again, encapsulation for electronics, solar panels. All of these are affected by very small amounts of moisture that would compromise the electronics or the functionality of these products. So we need a test method that is sensitive and accurate. So there's really two tests that facilitate very high moisture barrier testing. One very popular, especially for flexible electronics, is the calcium test, to where you actually use calcium as the detector, and you measure the conductance of the calcium hydroxide as the moisture passes through the barrier. It converts into calcium hydroxide, which changes the conductance of the sample. And then you can correlate that slope to a steady state water vapor transmission rate. And an instrument method, if you look at the schematic, it's very similar. It's very similar in look to the F1249, but it has a different sensor technology. So it has an absolute electrochemical sensor, and what this does is it essentially just counts water molecules. So you get great sensitivity and repeatability. Let's discuss a water vapor transmission rate case study for a company developing coated paperboard for beverage cartons. So in the packaging industry, what has become very common and very widespread is the sustainability push the word sustainability and packaging have become synonymous, over recent history here. And so we want things that are easier on the environment, so easier to recycle or something that can break down naturally and decompose. So you're getting a lot of coated papers, and papers that are not only coated with polymers, but also more so renewable things like different pulps, uh, even from things such as seaweed and sugarcane. I've even seen barriers that are placed within a slurry for a paper-based barrier. And so dispersed throughout that slurry, you get your barrier properties by creating a tortuous path. And also mono structures are just one material, so it's a lot easier to recycle. So keep it in line with the whole sustainability and ease on the environment here. This is a forecast showing compostable paper-based barriers, what the outlook is, and what the market is is going to be worth or spending towards this endeavor. It's the projected trend for the ease of recyclability. And as you can see, year over year from now currently in 2026, from 735 million to 2035 is actually 1.8 billion. So that's what is forecasted for steady growth into this marketplace or into this compostable paper-based barrier packaging materials. So this company, they produced coated paper, and they had a very successful thin craft paper that was coated with a barrier for oxygen and water vapor. And they wanted to make a paper board using the same barrier. So they had three different substrates. And as you can see, these substrates are porous when you look at the grain structure of the wood in them. And they want to coat these substrates and form a carton. So where did they start? What did they do? What did they notice? So they had a successful product, and they applied that same coating thickness to a much thicker paperboard substrate. They did some preliminary water vapor transmission rate studies and found that the coated paperboard with a much thicker substrate actually increased in barrier, and it increased in barrier substantially. So they are left scratching their heads like, okay, what's going on? We know that we have a decent barrier here, but why is it so much better when it's applied to a thicker substrate? So here are those preliminary results from some water vapor transmission rate studies at 23 degrees C and 50% relative humidity. So they all have the same coating thickness, same coating process. It's just the overall thickness is different because of the substrate thickness. So at the bottom there, you see their craft paper product, which is their flagship product. And that was 12 mils thick with the coating and the substrate. And for that, we got pretty repeatable results for water vapor transmission rate. And then for all the three other ones that they were developing, you had much better barriers, much lower water vapor transmission. So why would this be the case? So it really goes back to the porosity of paper. So that's just additional surface area within the structure that creates like a honeycomb for the coating to actually move into. So then when that happens, you get inconsistent coating thicknesses, you get more defects, pinholes, things of that nature. And with a much thicker substrate, as you can see in this drawing here, these arrows represent what we call edge diffusion. And the bigger the surface area is, the more pronounced potentially this edge diffusion, whereas you have your moisture source on one side, and as that moves into the film, that moisture, that, say, for instance, 50% relative humidity, that 50% relative humidity moves into the substrate, some moves out of the edges, and then the rest will move through the film and be measured. And this is the mechanism that was going on as to why the much thicker substrates had what appeared to be a much better barrier and a much lower water vapor transmission rate. That's because versus what you see on the top there, a much thinner substrate, you don't have all this increased surface area that is now available for your moisture to move laterally, because diffusion is non-directional. The molecules are just going to spread wherever they're going to spread. Nature takes the path of least resistance. So to remedy this situation of the moisture loss through the edges, this schematic here shows a good example of a film test, a flat film in a diffusion cell. And the one on the left, you see it has a lot of edge diffusion. And the one on the right is actually a modified cell that covers the edges. So essentially that forces any moisture that you're going to see by the detector. You know that that's moisture that actually permeated through the coating and was not compromised by atmospheric effects. Because that's another thing when testing these type of structures, depending on which lab you send it to. If it's not a controlled lab with the same relative humidity, at the time of year, you'll get different transmission rates because the ambient humidity is different. So you must always account for edge diffusion, or that has to be ruled out when you're designing these type of barriers. Okay, so once we ran all of these samples with the edges covered, uh, the data looked very different. Now that all the moisture is actually moving through the barrier, we are seeing that these water vapor transmission rates, they went up a lot. And now all three of the paperboard structures are a lot higher and have a lot less barrier than we thought at first, because they were having that edge issue there. So what was found was that there were pinholes present in half of the measurements that were done, which saturated the detector. That's why you have greater than 100, because it actually saturated the detector to where it could not read any more water vapor. And they also noticed that different labs are giving different results, because some labs were testing by covering the edges where others were not. Some labs had different ambient uh, relative humidity in them, and that also skewed the results. The next steps in the research and development process were to make sure that your coating is consistent and that your coating is thick enough to form a continuous layer. Otherwise, you'll have, those defect issues, and also a greater probability of thickness variation. So they took care of the coating process by just adding more coating. So I believe what was done was they took the ratio of the coating of the coating on their craft paper, the ratio of how much coating thickness to the thickness of that substrate, and then they used that same ratio for the thicker substrate, which worked in this case, and gave them a lot more consistency and better barriers. Because a way that I like to look at it when you're coating a porous structure is, if you have a screen door and you're spray painting a screen door with the spray can, what you'll notice is, a lot of the little holes in the screen won't have painting over them because, it went through. And that's kind of analogous to what was going on with coating a thicker substrate. So you have to keep spraying more and more coatings over it until the screen is actually adhering with the paint. So they shored up the coating process, did more water vapor transmission rate testing, found the best film and coating combination. Then they converted into a carton and they tested the whole carton because a package is a system. And once it's converted into this carton here, you have seams, you have closures. These things are potential leak points. So you really have to test the whole system and make sure that, these leak points have the barrier that they need, because it doesn't matter how high your barrier structure is if after conversion, you have leaky seams or the closure isn't sealing properly, and then permeation is just going to find the easiest path, which I like to use the analogy, the weakest link in the chain.